Hi, this is Group 3, What Do Fugacity, and I'm Louis Wera. My group members are Liska, Mei Ying, and also Winners. And this is our 470 senior design project. So to begin, I'm just going to give a little overview about the entire process and the point of this presentation. We're going to hit 4 major key points we're talking today, and they are the product specifications, the process overview, the economic evaluation, and also our final recommendations. So I'm going to get started with a little bit of general information for you guys. So the whole point of this project was to create a plant that will produce saleable grade purity of 99.9% grade acetone. And we did achieve that. We're producing 99.9% weight pure, and we're also producing at a capacity of 142 million pounds per year. A side product of our facility, we're also selling our acetic acid, which is also up to saleable grade, as seen here at 99.9% weight. And the June startup at 2021, and we're also located in Houston, Texas. So to start, I'm going to talk a little bit about product specifications. As seen in the figure right on the right-hand side, that we are in fact reaching a 99.9% weight acetone with little contaminants. As seen here, the only thing else is in there is 2-propanol, and that had to be under 5 ppm, so we did reach that spec. On the figure on the left, that shows the total mole percent recovery of acetone we reached in the feedstock. As you can see, we did in fact reach a spec of 95% mole recovery. Another soft spec that we did reach was we were under 4,000 BTU per pound acetone produced. That was just summing up all the reboiler duties of, within the process that did not in fact refine a secondary product. So we were underneath that. I think we're around 2,000 BTU per pound acetone produced. And so the next thing, Winners will talk about the block flow diagram.
Hi, I'm Winter School. Next, I'm going to talk about the block flow diagram. There are 6 different phases in our total design. The first phase is the removal of acetic acid. As we know, acetic acid has a pH value of 4.53, which means it's really corrosive for carbon steel. As a result, that's one of the big challenges we're facing in our design because in order to reduce the overall cost on the equipment, we have to remove the acetic acid first. That's why we have to use 304 stainless steel in the first distillation tower, which is called SSDT1. Next phase is the reactor, where the generation of the acetone happens. So there's a soft requirement is to reach 95% more of recovery from IPOH to acetone. In order to reach that soft requirement, we decided to introduce a recovery stream from the phase 6 into the reactor. Next phase, I'm going to talk about the gas separator, the removal of the hydrogen and propane. As the reaction happens, not only acetone is produced, but also the hydrogen and propane, which are 2 highly flammable gases. So in order to remove them, a gas separator is designed. Thanks to the gas separator, at the bottom of the stream, we can reach to 0.00060 weight percent of propane and absolutely 0% of the hydrogen. So after that, there will be no more highly flammable gas in the entire plant. Next phase I'm going to talk about is the separation of the methanol acetone mixture from other chemicals. Methanol and acetone, they have really close boiling points, but they have really big difference compared to any other chemicals. So that's why we designed to remove the methanol acetone mixture first at the phase 4. Next phase, we're going to talk about the purification of the acetone. The biggest design we have right now is the purification of the acetone, because acetone and methanol mixture would generate an azeotrope, really difficult for us to reach 99.9% of the purification. In order to break the azeotrope, we designed a high-low pressure system to break the azeotrope. Thanks to that system, eventually we can reach to a production rate of 16,950 pounds per hour with a purity of 99.9 weight percent. And in order to reach the last requirement, which is 95% more acetone recovery, we designed the last phase, which is the IPOH recovery. So the IPOH recovery would conduct at SSDT5. Over there, we're going to have a IPOH recovery stream going back to the reactor. So that's the entire design of the 6 different phases of the block flow diagram. Next thing, I'm going to talk about the safety and the environment. Safety is always the #1 priority. That's why personal protection equipment is mandatory for all the employees. And in the entire plant, formaldehyde is the most toxic chemical, and it has the health hazard of 3, flammable of 2, and it has the LD50 of 50 333 ppm, which is the lowest among all the chemicals. And that's why a respiratory protection system is mandatory for all the employee who works on the floor. Next thing we're going to talk about the hydrogen. Hydrogen is the most flammable component in the system. In order to reduce the safety hazard in the system, we decided to build a flyer system to burn down the propane and the hydrogen. So the combustion of the propane and hydrogen would only yield water and carbon dioxide, which are non-hazard to the environment. So we are confident to say that the gas we're burning out of the system are non-hazard to our environment. Next section would be cost analysis, and Mengying will bring that to you guys.
So right now, our total plant cost is like $77.8 million per year. And our OBL is $36 million per dollar. And OBL is $25 million. Other costs includes taxes, insurance, and labor costs is $16.8 million per year. As we can see in the pie chart, these three costs split up pretty well in the total cost. IBL, or it stands for inside battery limit, and it's basically just the capital cost. In this chart, it shows every single equipment cost in our plant. But we can see SSDT1, SSDT2, and gas separators, they made up most of the IBL cost. This is mainly because the temperature requirement, the material we're using, and the heavy duty on the condenser and we blow apart. And next, we're gonna switch back to Liska, and she will talk about the OBL.
So Mengying talked about the IBL, or the inside battery limit. Now, I'm going to talk about the outside battery limit, or OBL, that represents the non-process or infrastructure that are necessary to support our processes. Generally, it includes product storage, utilities, which are cooling tower and boiling system upgrades, site development, and environmental that includes flare system. The biggest cost that we have right now in the OBL is product storage, which is $7.25 million, followed by the cooling tower, $6.72 million, and then boiler system upgrade of $2.52 million. The reason why product storage contributed a huge amount of cost is that we need to store a large flow rate of acetone and also formaldehyde and acetic acid that are corrosive and need special, more expensive tank made of stainless steel SS304. While the OBL and IBL represent the capital cost, there is also an operating cost that we have to pay in order for the processes of the plant to operate properly. It includes waste, labor, overhead, repair, maintenance, taxes, utilities, and other features that support the operation of the plant. From our design, as you can see here in the pie chart, the largest amount is the waste cost that takes up to 48% of the whole operating cost. And this is due to the need to handle such large amount of waste. It is then followed by labor and overhead and utilities. Many plants have a large amount of utility cost, but our energy integration system reuses a lot of other process streams, and that actually cut down the utility costs to make it 17% of the whole operating cost. From our design, the plant operates for 15 years after 3 years of building, and it will shut down in the year 19th. An internal rate of return of 76.9% is achieved by our model. As it is significantly higher than the 15% requirement, it is profitable to build this plant. Moreover, the net present worth is $236.7 million. To achieve a required netback, acetone product can be sold for as low as 25.4 cents per pound, even though currently, based on our prediction, acetone can be sold for 73 cents per pound. Mengying will talk more about the alternate processes that can be done with our plant.
Okay, so another thing we can do to design the plant is to eliminate acetic acid first by adding sodium bicarbonate in the waste stream. As we all know, like acetic acid is pretty corrosive, so we have to use stainless steel to store or to process acetic acid in order to prevent corrosion. But the price for the stainless steel is pretty high. So if we can eliminate acetic acid first, we can reduce the capital cost greatly. So this bar chart shows the material and manpower and equipment and setting costs if we do the alternative study. Although remove acetic acid first can reduce capital costs, but the study from Lawrence Shorosky shows that we can make more money by selling acetic acid than our alternative study. So next, Luis will talk about the recommendations.
Hi, so I'm just going to give a little bit of recap today. So our plant is stationed down in Houston, Texas. It has a June 2021 startup date, and we are producing saleable grade 99.9% weight acetone at a capacity of 142 million pounds per year. As a side product, we are also producing acetic acid, which is also saleable grade. Our current company's net percent worth is $237 million, and that's after 19 years of operation. That's including the 19th year being the shutdown date. Our main safety concerns are formaldehyde and our H2. Just because formaldehyde at the concentrations that we have, it's above the lethal dose. So if any leaks happen, we really can't have too many people on the floor. If they're on the floor in that area of the plant, that they're going to need to be full hazmat gear and air respirator. And also with the safety concern with H2 is pretty common sense. That's all about the flammability of it. Any leaks, open spark. If there's anything, nature's going to provide that spark, so we just have to be careful with that. As proved in the alternative study slides before this, sodium bicarbonate could be used as a very useful thing to neutralize acetic acid, so you don't have to purchase a stainless steel distillation tower. But as proved in the alternative study, it's saving on the capital cost, but that $1.3 million per year generated from the acetic acid stream is a pretty good revenue for our company, so we decided to go against it and leave it in. Our final recommendation would be go ahead and build the plant. Just because of the great success and revenue that we have and our net process worth. But our main concern would be try to get our total waste cost down. Currently the waste costs are at 48%. That's mainly because we can burn the methanol stream, but we really can't burn the method oxide water waste, just because one, it's half, I think it's 50% formaldehyde, and also there's a lot of water in that stream. So I think what we need to do is maybe decrease the temperature on the reactor, or try to completely remove the methanol before it goes in the reactor, because the methanol conversion to formaldehyde is what creates that in the system. So if you could remove that methanol contaminant, it would also be easier down the road getting out of acetone too. So just to recap, go ahead and build it. I don't know what to say now.
All right, that's enough. That's enough of that.